So there's the people that are here. Okay, so let's just get on with it. This is doing projectiles in an inclined plane. So we've done projectiles on a flat plane, and you were asked to do questions 3A and 3B. And I don't suppose that they caused much in the way of a problem. We have to remember a few things. One, that the range is equal to the distance along the I at the time that the distance in J is equal to 0. And that's crucial. And that doesn't really change. And we'll see a little issue in a minute. And the other thing that they can also ask you is about the distance in J. So they can say to you, what's the maximum distance in J? Well, you might remember at the max distance in J, that the V of J is equal to 0, which implies that the U of J squared is equal to twice GS. And that's all well and good. That's really up and down. There's a few other things they can ask you about hitting targets, which is again to do with your S of J, your S of I. You're also going to need to remember your V of I and your V of J. You need to be able to write those phrases and those formulas. And that's really the crucial part to it. But let's come back to this. The problem we have here is that we now have an inclined plane. We have, in this case, a projectile that's been shot up an inclined plane. You can also have a projectile been shot down an inclined plane, and really and truly things don't change too much. What governs something falling, though, is gravity. So we got to draw in the vector of gravity, and that goes straight down. And that's G there. Okay. Now, that's okay. So we can say that this hill, that the hill is inclined at an angle alpha to the horizontal, and that the angle of projection to the inclined plane is theta. Is that all right? That shouldn't change too much. The thing I've got here is that really and truly, I don't want to deal with I's going this way and J's going this way anymore. That's not going to help. If we come back to our phrase for range that says that it's S of I at the time that S of J is equal to 0, we can keep that if we say that this here is our I-axis, and if this is our I-axis, well then our J-axis is now perpendicular to the surface of the plane. Is that okay? And that makes a few little changes to a lot of the formulas. I said a few little changes to all the formulas, maybe be a better way of putting it. What I should do right now is I should just put in the vectors that G can be now comprised of. And there's two of them. One that goes parallel to the plane and one that goes perpendicular to the plane. It turns out this angle here is alpha, and so this here is G sine alpha, and that's in the I. And this one is going now is G cos alpha, and that's in the J. Is that okay? Oh, Roshan. Roshan's out there. Come on. Yes. Right, so Roshan, you should be coming in some stage unless she's decided it wasn't worth it. If any of you are there, please do say hi, and I'll stop you if you have any questions. It'd be great if I could hear you, but I can't hear anything now. Maybe you send me an email if that's the case. I don't know what's happening now. I'm after messing up things. Yes, I'm going to go back here and stay here. I did test the sound and the audio for me. I could hear it, so I'm really hoping that you can hear it too. Yeah, okay. So that's the crucial bit, okay? That we now have an angle alpha to the horizontal for the plane. Still the same angle of projection, theta, for the projection. And now we just got to deal with this G sine alpha and this G cos alpha. Is that okay? I'm going to skip page and come back to all this in a moment. We can just use it as a reference back and forth. Is that okay? Right. I'm nearly sure I told you that very, very handy thing to write for these formula when you're doing these questions was the V of I and the V of J and the S of I and the S of J. Okay, and they're not very clearly coming out on that screen, so I'll do it again. So the main general formula for V is equal to U plus AT, and S is equal to UT plus a half of A times T squared. Yes, you should remember them. Let's just put them in terms of, oh yes, Louis, what happened to you? So I don't know who's here and who's not here. Oh, someone just closed the door. Hello. Can't hear. Can't hear and can't wait. 7 minutes into this. Okay. The V of I. V of I is dealing with the U of I plus the acceleration in I by the time. Is that all right? Let's go back to the picture. The U in I is going up here, and so therefore it's really this side here. I'm drawing it in blue, or I'm drawing along there. And you should be able to figure out that that's equal to U times cos theta. Okay? So V of I is equal to U cos theta. Theta, not alpha. Plus. Well, is it really plus? The G in the I is coming back this way. So it's going to be a negative. Is that all right? So that's minus G. What did I say? What did we say it was? G sine alpha times T. Is that okay? Hope it is. I can't hear anybody, so what heck. V over Vj, the velocity in the J, is equal to the U in J plus the acceleration in J by the time. Again, this time it's equal to U. You can hear sine theta. You can nearly always expect it to be the opposite when you go from I to J. Again, minus, because the U sine alpha is going upwards. Should be going up like this. And the gravity is coming down. Now, there is, of course, the scenario where you kick a ball down a hill. It obviously goes further than it would if it was flat, and that's because we're adding it, but that's different. So this is equal to G cos alpha times T. The S of I is very similar. It's again dealing with the U, same U, so it's U cos theta T minus G sine alpha all over 2 times T squared. And S of J is equal to U sine theta T minus G cos alpha over 2 times T squared. And that really is everything you need to know. My advice to you when you're answering a question is that you should draw the diagram, and the diagram should look something like this. Especially all the red and blue lines I've got, where you got your initial velocity going up, your angle to the horizontal, and then your angle of the inclined plane. Draw gravity in this time. Oh, 2 people are waiting. Sorry, ladies. Sorry for leaving you waiting. Where am I going? Back here. Sorry for leaving you hanging. It'll all be recorded and put up somewhere soon. So, where was I? When you're starting a question, you want to draw what you have, which is your initial velocity going up, your angle that it makes to the inclined plane, the angle of the inclined plane indicated. We'll get to examples later. Is that you, Christine?
Yes.
Hi.
Hi. Did you see me, sir?
Kind of. You look like you're on your side.
Where's me?
Maybe it's just a picture. It doesn't look like it's moving.
That's not me.
You can see
On your
me?
pic. Yes.
You can hear me clearly?
Yes.
Deadly. Cool. Right, I'm going to keep going. This will all be recorded. We'll try and cut out that little bit, though, will we? I think so. Excuse me. So, we have that drawn, and then we want to have, we want to do what we want to do, which is often find the range. So if that's the case, it's still the distance in I at the time that the distance in J is equal to 0. I said earlier we're going to turn it. We're going to turn our world around so that our I's go along this way and our J's go along this way. It turns the world around, but it shifts G's ever so slightly. So we've now got G in the I and a G in the J. That leads us to these equations. If you're watching this now or you're watching it later, maybe take a snapshot, but that's pretty much what you've got to achieve. Is that all right? So without much further ado, there's not really much point in me just waffling on. I think I've looked at the entire set of problems we're going to come up with. So now let's look at some problems. Yeah. So I'm going to go back to the book. I'm going to go to page 96. This chapter starts on 95. He talks about that and that, and he talks about that and that. He does it a slightly different way to the way I'm doing it, but I'm okay. Same things in general. Okay. Example 3C1. The particle is projected up a plane inclined 30 degrees to the horizontal. The initial velocity of the particle is 45 meters per second. The line of projection makes an angle of tan 3/4 with the inclined plane. The plane of projection is vertical and contains the line of greatest slope. This you will see all the time. This can be ignored. It basically says that the game is fair. That's all it is. It's like an assumption you don't really require. Okay, so first thing to do is to draw the scenario I've got. Reading the question, example 3C1. I've got a horizontal here. I'm going to shift an inclined plane in here. It goes up at 30 degrees. There's a projectile then is fired here, and the speed they gave us was 45 meters per second. They said this angle here, I didn't give it theta, but I'm going to give it theta. That's not very clear, is it? Is it better without the light? It is better without the light. What do you think, Christine? Better with the light? Have you muted yourself?
Yes.
Thanks.
Yes, sir.
Cool. Thank you. You're the only person who's talking, so we'll take it that. It says that tan of alpha is equal to 3/4. I've told you this before. Whenever you get a tan of something, try and find out the sine and cos very quickly. Those who paid attention in class will know the 3 squared is 9 plus 4 squared is 16. And 2 of them 25. Root of that is 5. So therefore, sine is 3/5, and cos is 4/5. That's very handy. You'll see why shortly. Okay. So the next thing I'm going to want to draw in is G. I'm going to show that gravity falls downwards with an angle there. Gives me a J component, a J component, and an I component. Remember, we're now dealing with I's this way and that, and J's are dealing with up and down. Okay, we just upside in your head, I think is what I said before, and people got that right. So, right in the initial terms, the unit vectors along the perpendicular to the inclined plane. So this is going to 45 degrees. I want to find out the I's and the J's. So this really is hypotenuse times cos alpha, and this is hypotenuse times sine alpha, which is 45 times cos, which is 4/5, 9, which is equal to 36. I hope you get that. I'll do it again anyway. Hypotenuse is 45, given up here. Sine alpha, we said was 3/5. 3/5 of 45 is 9/927. Again, folks, you use a calculator. I just done these questions so many times that it's just, it's mental arithmetic at this stage. Is that okay? And that's it. So this is really 36I, and that is really 27J. That's the initial velocity in terms of I and J along and perpendicular. Okay. Now, where is this? That's the A part. It's the I part of the example. Second part says, what are the accelerations? Well, what's causing acceleration? The only thing that causes acceleration of projectile is actually gravity. So in this case, here is G. This is G. I'm muting you. Yes. This is G times sine 30. And this is G times cos 30. For those who think I'm cruel, I'll unmute her when I get to some questions. Is that okay? So in the I, this vector is going back down, and it's now going to be G times sine 30. Oh, hi, Salma. Excuse me. It's going to be G sine 30. And then in the J, going down. Hi, Salma. No, are you there? It's going to be G cos 30. I know that G cos 30 is equal to half a G, and then this is equal to root 3 G over 2. That's the very best of mine. Is that okay? And I hope they're visible to you. I should really get rid of all this. But sure, there you go. Is that all right? So they are the accelerations. This one is going back down the inclined plane, and this one is going into the inclined plane. And there are J's and I's. Is that all right? Okay. The next part, it says, and sorry, I'm on page 96. I'm doing example 3C1, and I'm on part 3. And it says, find the time of flight for the projectile. The time of flight, I've got about 15 minutes to go. The time of flight is the time at which S of J is equal to 0. So I need a phrase for S of J. Oh, look, here's one I made earlier. Again, these are back in earlier in the video. I think I described accurately how to make them, but this is our formula. U sine theta J minus G cos alpha over 2 T squared. Theta is the angle of projection against the inclined plane, and alpha is the angle of the inclined plane to the horizontal. Again, I'm making sense to me. I hope I'm making sense to you. Okay, so let's just get that out. So we're saying that S of J is equal to U sine theta T minus G cos alpha over 2 times T squared. We said that was equal to 0. That's how we know something lands. I should really flip this around there. That makes it easier for you. Anyway, so therefore, if that's equal to 0, that implies that U sine theta T is equal to G cos alpha all over 2 times T squared. Something common on both sides? Yes, big old T. So divide that side by T and divide that side by T, and we're getting a bit closer. We get 2 U sine theta divided by G cos alpha is equal to T. They asked me to find T. So we've got to use what we do know in this question. We're going to put in what we have. So 2U sine theta, well, I should have this earlier, was Oh, actually, I've called it the wrong thing. 27, so 54. 54 over G cos, wrong thing. So that's G, root 3 over 2. Okay, is equal to T. So that makes dividing by, oh, sorry, off the screen. 54 divided by G root 3 over 2, which makes 108 over root 3 G. And that's in seconds. That's a number. It might not look too much like a number, but it is a number. And that number is 108 divided by root 3 divided by 9.8. And it's 6.36 seconds, okay? Equals 6.36 seconds. It then says find the range along the inclined plane. I'm going to just start a new page. We said previously, we said the whole way through this section, the range was always given to us by the distance in I at the time that S of j was equal to 0. Well, the time of S of j equals 0 is equal to 6.36 seconds. The range in I was equal to S of I. Again, let's go back to this. This is the notes we wrote a couple of minutes ago. The distance in I is u cos theta t minus g sine alpha divided by 2 over t squared. So S of I is equal to u cos theta t minus g sine alpha over 2 times t squared. This is the initial speed in the I. Back from the last page, I said that was 36I. So 36 times t. I'll come back to that. Minus minus here, minus g sine 30. So that's g over 2. So it's g over 4. It's g over 2 divided by 2, 4 times t squared. Okay. So now that's equal to 36 times 6.36 minus g over 4 times 6.36 squared times 36 equals 229 meters minus 6.36. Oh, 6.36 squared times 9.8 divided by 4 minus 99. So plus 229 gives me a total of 130 meters. And that, I'm hoping, is the right answer. Yeah, 129.9 is what they're giving us in the book. I should have not rounded, but I did, and I'm not too upset about it either. So it then says find the velocity which it lands in the plane in terms of unit vectors and perpendicular to the plane. Really, truly, this isn't a big question. It's not a common question. Really, what we're doing here is we're looking for the VI and the VJ, and we did have them. I wrote them out on the first page that I've shown you a number of times. These two phrases, they're a lot more simple than the last two. So I'll write them out again. VI is equal to U cos theta minus G sine alpha T and U sine theta minus G cos alpha T. I want to find both of those values. That's going to give me the V and I and the VJ, of course, and then I want to find the speed. So we'll talk about that just one moment, right? So U cos alpha is the speed it was going along in the I, which we said was 36I. So VI and VJ. I'll just be lazy. So 36I, 27J minus the acceleration. So the acceleration here was g over 2 at landing. At landing was 6.36. And then it was minus root 3 g over 2 times again 6.36. Okay. 36 minus. Right, cool. Yeah, great. Love it. Thanks. Oh, there's Louis. Yeah. I'll do which is all in a moment anyway. 36i minus 4.9 times 6.36 is 36i minus 31.164i, which can't be much, plus 36. 4.8i, and the VJ is 27i, 3 root times 9.8 divided by 2 times 6.36 is 53 minus plus 27. So the VJ is equal to minus 27 meters per second. That makes sense, by the way, on most of these arcs, because the speed up should be equal to roughly the speed down. But we'll come back to that again. That's so. If it's to draw a vector, I've now got this real small I vector. That excuse me. My inclined plane looks like this. My I vector is this one. That's the 4.8, and then it's also been added to this 20 minus 27, and so we get this vector here. So this is 27 squared plus 4.8 squared, and get the root of all that. Square that plus 4.8 square that equals 750, and then get the root of that, and I get back to it. So V is equal to 27.4 meters per second. Okay, so that's the example, example 1. Okay, so I suppose it's to you guys, really. Let's try and bring everybody back in. I think I've got somebody muted. Unmute Christine. Hi, Christine.
Hi, sir.
How are you?
Good.
Did you follow that?
Yes. But how did you get 27.4?
This.
Yeah.
So see the way this vector here is coming down to 27.
Yeah.
And this vector here has gone off of 4.8.
Yes.
Well, I just used Pythagoras. So I squared this, squared that, added the two together, and got the root of it. And that gave me 27.4. I was letting that sound in. Anybody else? Any comments? Nobody else there. Louis, can you hear me? I can see you, Louis. Have you not got a microphone? If you do, it's not working. It's probably the best way to have Louis, really, isn't it? Okay. Long and the short, really, folks, is, I'll recap the whole thing, but long and the short of this is really you need to be doing the 20 minutes. The crisis we're going through is unprecedented. The crisis we're going through is also never, any other crisis that's never had digital communication like we do. We should use this to the maximum. Do your 20 minutes every day. It should be a lot easier considering you don't have to go to school. You can do it in your pajamas if you so want. Don't want to know about it if you do. Do them and send me messages. I'm going to use this Microsoft Teams. There's lots of me hating it, but I'm going to use it. So I'm going to try and check in every day. Send me where you are. Tell me where you get stuck. I won't say, oh, it was Margaret. I will just get on with it and try and do it as quickly as I possibly can. Make YouTubes and stick them up there for you. Is that okay? I'd love to solve these problems for you. I'd like to be helping you. And that's what I need to do. Before we go, let's go recap the whole thing again, okay? Right. What we're dealing with in this section, 3C, is projectiles on an inclined plane. Projectiles on an inclined plane are not much different to projectiles on a flat plane as long as you upside your head. What I mean by upsiding your head is we're going to turn our head around so that this is now the baseline. If we do that, that's fine. We now make this the I and this the J. As I said earlier, gravity doesn't change, and so gravity's still coming down the way it was to the original plane. So how do we fix that? We resolve G into J's and I's. This side here being G sine of the angle that the hill is to the horizontal, and this being G cos of that angle. I hope that's okay. Following that the range is equal to still the distance along I at the time that the S of J is equal to 0. So when it comes down, it's still the distance along. Okay. Yeah, so I'm happy with all that, and I think you should be. Crucials. I tried to say this to you in the last two sections, in the first section. Write down a full phrase for S of J. Write down a full phrase for S of I. Write down a full phrase for V of I and a full phrase for V of J. If you do that, you are pretty much in good shape. If you're lazy, I would definitely write down SJ and SI and leave VI and VJ until you need them. Why I would do them now is because you may need to call about them in an exam. If you need to call about them in an exam, you need to have that practice. Is that okay? That's all I think. Okay, so that's that. It's the wrong page. These are the phrases. It is so terrible. Do not copy this. Just per se. Know where it came from. This is the general equation V and S that your physics teachers would have showed you. Anyway, is that all right? So V is equal to U plus AT, S is equal to UT plus a half AT squared. We did this in linear motion. And so this kind of got to be down. Okay. This is when I turn it into the vector of I, and this is fully expanded out using UI as broken down into the angle U cos. When I get U and I get the cos of it, and I get G and I get the sine of it. These are the ones in the I's. VJ is U sine, that's U sine, and U and G cos. Okay. SI is the same comparisons, it's just a different formula. Okay.